Download this code from codegive.com, link in the description below. OK, let's dive deep into memory alignment and undefined behavior in C and C++. These are crucial concepts for writing efficient and reliable code, especially when working with low-level programming, data structures, and performance optimization. Part 1, Memory Alignment. What is memory alignment? Memory alignment refers to the requirement that data of a certain type must be stored at a memory address that is a multiple of its size. In simpler terms, an int, typically 4 bytes, might need to be stored at an address that's a multiple of 4, example 0x1000, 0x1004, 0x1008, etc. A double, typically 8 bytes, might need to be stored at an address that's a multiple of 8. A short, typically 2 bytes, might need to be stored at an address that's a multiple of 2. The exact requirements are determined by the target architecture, CPU, and the compiler. Why is memory alignment necessary? 1. Performance. CPUs can often access aligned data much faster than unaligned data. When data is aligned, the CPU can fetch it in a single memory operation. Unaligned data might require multiple memory accesses and potentially extra processing by the CPU, significantly slowing things down. 2. Hardware limitations. Some architectures might have restrictions that require aligned access. Trying to access unaligned data can lead to hardware exceptions, like a bus error or segmentation fault, and program crashes. 3. Atomicity. Aligned access is often required for atomic operations, which are used in concurrent programming to prevent data races. Atomic operations need to be able to read and write entire data values in a single, indivisible step. How does alignment work? The compiler is responsible for ensuring that data is properly aligned. It does this by inserting padding. When defining structures or classes, the compiler may insert extra bytes, padding, between members to ensure that subsequent members are aligned. Alignment of variables. The compiler ensures that variables declared in functions and at the global scope are placed at properly aligned addresses. Code example 1, structure padding and alignment. Explanation. Size of, struct mystruct, on many architectures, x86, x86-64, the size of mystruct is likely to be 8 bytes. Why not 1 plus 4 plus 2 equals 7? Because of padding. Offstuff. This macro, defined in stef.h, tells you the offset, in bytes, of a member within a structure. A is at offset 0. B is at offset 4. The compiler inserted 3 bytes of padding after A to ensure that B is aligned to a 4-byte boundary, because int is 4 bytes. C is at offset 8. The compiler inserted 0 bytes padding after B to ensure that C is aligned to a 2-byte boundary, because short is 2 bytes. The final size of the struct is then padded out to be a multiple of the largest alignment requirement, in this case, the size of an int. How to change alignment, attribute and pragmas. C and C++ provide ways to influence alignment, although the specific syntax might vary slightly depending on the compiler. Asterisk underscore underscore attribute underscore underscore, aligned, x, gcc/clang. This attribute can be used to specify a minimum alignment for a variable or structure member. Asterisk pragma pack, x, Microsoft Visual C++. This pragma allows you to change the packing alignment of structure members. Be very careful when using pragma pack, as it can lead to compatibility issues if different parts of your code are compiled with different packing settings. Code example 2, using alignment attributes. Explanation asterisk. Asterisk underscore underscore attribute underscore underscore, aligned, 8. This tells the compiler to ensure that align struct is aligned to at least an 8-byte boundary. This might result in the struct being larger than it would otherwise be. Asterisk the address of my var will be a multiple of 8. Code example 3, Pragma Pack, Windows/Visual C++. Explanation asterisk. Asterisk Pragma Pack, push, 1, this saves the current packing alignment and sets it to 1 byte. This means the compiler will not insert any padding between members. The size of pack struct will now be exactly 1 plus 4 plus 2 equals 7 bytes. Members will not be aligned. Asterisk Pragma Pack, pop, this restores the previous packing alignment setting. It's good practice to push and pop to avoid affecting other parts of your code unintentionally. Asterisk accessing B and C might be slower, or even illegal on some architectures, because they are unaligned. Asterisk important note asterisk using Pragma Pack, 1, can lead to performance degradation and potentially cause crashes on architectures that strictly require aligned access. Only use it if you have a specific reason, example interfacing with external data formats. Why is alignment important in practice? Asterisk networking asterisk when dealing with network protocols, data is often packed in a specific format. Using Pragma Pack might be necessary to correctly interpret network packets. Asterisk file I/O asterisk reading and writing binary data from / to files might require specific alignment settings. Asterisk memory mapped I/O asterisk when interacting with hardware devices through memory mapped I/O, alignment is often crucial. Asterisk optimized data structures asterisk in some cases, you can optimize the layout of your data structures to reduce memory consumption and improve performance by carefully considering alignment. However, this often comes at the cost of code readability and maintainability, so balance is important. Asterisk SIMD, single instruction, multiple data SIMD instructions often require data to be aligned to specific boundaries, example 16-byte alignment for SSE, 32-byte alignment for AVX. If data is not aligned correctly, SIMD operations may crash or produce incorrect results. Part 2, Undefined Behavior. What is undefined behavior? Undefined behavior, UB, is a term used in the C and C++ standards to describe situations where the language specification does not define what should happen. When a program exhibits undefined behavior, anything can happen. The compiler is free to do whatever it wants. Asterisk the program might appear to work correctly, most of the time. Asterisk the program might crash. Asterisk the program might produce incorrect results. Asterisk the compiler might optimize the code in a way that leads to unexpected behavior. Asterisk the program might do something completely unpredictable, example format your hard drive, highly unlikely, but theoretically possible. Why is undefined behavior bad? 1. Unpredictability asterisk UB makes programs unreliable and difficult to debug. The behavior can change from compiler to compiler, architecture to architecture, or even with different optimization levels. 2. Security vulnerabilities asterisk UB can be exploited by attackers to gain control of a system. Compilers might make assumptions based on the assumption that certain UB conditions will never occur, and attackers can then violate those assumptions to inject malicious code. 3. Compiler optimizations asterisk compilers are highly aggressive in optimizing code. If the compiler detects UB, it might assume that the code is impossible and make optimizations that completely change the program's behavior, often in unexpected ways. This can lead to very subtle bugs. Common examples of undefined behavior asterisk. 1. Accessing memory out of bounds asterisk. 2. Dereferencing a null pointer asterisk. 3. Signed integer overflow asterisk. 4. Modifying a string literal asterisk. 5. Using an uninitialized variable asterisk. 6. Data races in multi-threaded code, without proper synchronization. 7. Incorrectly aliasing pointers asterisk. 8. Shifting by a negative amount or more than or equal to the width of the type asterisk. How to avoid undefined behavior asterisk. 1. Understand the language standards asterisk. Read and understand the C and C++ standards, or reliable documentation. Know what operations are defined and what operations are undefined. 2. Use static analysis tools asterisk. Static analysis tools, example Clang Static Analyzer, Covrighty, PVS Studio, can detect potential sources of undefined behavior at compile time. 3. Use address sanitizers and memory checkers asterisk. Address sanitizers, example address sanitizer, ASAN, and memory checkers, example Valgrind, can detect memory errors, example out of bounds access, use after free, at runtime. 4. Be careful with pointers asterisk. Always initialize pointers to valid memory locations or null. Check pointers for null before dereferencing them. Avoid pointer arithmetic unless you fully understand what you are doing. 5. Be aware of integer overflow asterisk. Check for potential integer overflows before performing arithmetic operations. Use wider integer types if necessary. 6. Use safe string handling functions asterisk. Avoid functions like strcpy and sprintf, which are prone to buffer overflows. Use safer alternatives like strncpy and tinprintf, and always provide a maximum length argument. 7. Use mutexes and other synchronization primitives asterisk. In multi-threaded code, use mutexes, semaphores, atomic variables, and other synchronization primitives to protect shared data from data races. 8. Compile with wall_extra_warrer asterisk. These compiler flags enable more warnings and treat warnings as errors. This forces you to address potential problems early in the development process. 9. Enable optimization, but test thoroughly. Compilers are often better at detecting UB when optimizations are enabled. However, optimizations can also make UB more apparent, or harder to diagnose, because they can change the program's behavior in unexpected ways. Test your code thoroughly with different optimization levels. 10. Be suspicious asterisk. Always be critical of your own code. Assume that there are bugs lurking. Review your code carefully, and ask others to review it as well. In summary asterisk. Memory alignment is about efficiently placing data in memory based on its size, affecting performance, and sometimes correctness. Undefined behavior is when the language spec doesn't guarantee what will happen, leading to unpredictable and potentially dangerous outcomes. It's crucial to avoid it. By understanding these concepts and using the tools and techniques described above, you can write more robust, reliable, and secure C and C++ code. Good luck.